Good evening, ladies and gentlemen, wherever you are. So an inaugural lecture is a very old academic tradition. In 1669, Professor Isaac Newton was appointed to the Lucasian Professor of Mathematics at Trinity College in Cambridge. And he spoke on the topic of colors. Now, Newton, of course, is known very well for his theories of mechanics and gravitation, but we also know from the time we spent in school that he also did work on optics and colors. Over 300, Professor Stephen Hawking was appointed to the same Lucasian chair of mathematics at Trinity College, and he spoke in his inaugural lecture on the topic, "Is the end in sight for theoretical physics?" So, to have an inaugural lecture, when the university promotes an inaugural lecture, it is standing in the line of a long tradition. The second thing that I want to say is that, in the early days, the word professor was used rather indiscriminately. In the very early days, anyone who taught was also called a professor. And I think in Italy, we get this same idea because any teacher is called professori. But in the English-speaking world, now there is a very clear distinction between people who are professors and people who are just normal lecturers. So I think there are a few differences between lecturers and professors. The general audience for a lecturer is a group of students. Whereas where a professor is concerned, when the university bestows the title of professor on one of its teachers, it means that that person is ready to face the world. And his audience is the public, is the world. Lecturers, when they teach students, they generally tell students about established knowledge. It is a dissemination or transmission of established knowledge. But professors are expected to discover new knowledge and be at that cutting edge of knowledge. In lectures, generally what is covered is in the area of facts. It is facts that are transmitted to students. But professors are expected to develop theories, and a theory is something like a belief, because the word profess is often used in the context of a belief. What I profess, what I believe, the theories I hold. And we expect of professors that they will hold theories, because a theory is something that is held without undue regard to everyday experience, right? So, for example, Nicolaus Copernicus, although every morning, like the rest of the people during his time, he saw the sun rising in the east and setting in the west, he was bold enough to say that although this is what things appear to be, actually it is the earth that is turning around its axis, and the earth is going around the sun. And more recently, Sir John Baker, who was professor of mechanical sciences at Cambridge University, was bold enough to say that when we design structures, we should not look at the way that they normally behave, but think about the point of failure, and so gave rise to a whole new theory of plastic design. So professors are expected to hold beliefs, to profess those beliefs, and to be able to defend those beliefs in front of the public. Thank you.
Hi everyone, very good day. Well, welcome to another inaugural lecture where we are introducing another one of our professors. And to introduce the speaker today, may I invite Professor J.R. Lucas. It's nice to see you, sir, here at University today. So over to you, Professor Lucas, to introduce today's our professor.
Thank you, Ajit. Good evening. Vice Chancellor Professor Niranjan Gunawardena, Deputy Vice Chancellor Professor P.K. Mahanama, Dean Faculty of Engineering Professor Nalin Vikramarati, Dean Faculty of Graduate Studies Professor Ajit Dialvis, Professor Anura Wijayapala, staff members of the University of Morocco, and distinguished guests. It gives me great pleasure to introduce my colleague, Professor Don Anura Senaka Wijayapala, on the occasion of his inaugural lecture as part of the lecture series of the Faculty of Graduate Studies of the University of Morocco. Anura, as is commonly known, graduated from the Electrical Engineering Department of the University of Morocco 30 years ago. Anura was among the best in his batch, and I was then pleased to recommend him for employment as a development engineer at the fledgling Lanka Transformers Limited, as I felt that to be a good teacher in electrical engineering, it was necessary to get first-hand experience working in an electrical engineering concern. Anura proved my faith in him and first rose to become the factory manager of Lanka Transformers Limited within 1 year. Then the government of Sri Lanka introduced a major policy shift in power sector by allowing private investment for power plants in the CEP system. Anura was taken off from the transformer factory and made the project manager to guide the formation of Lakdanavi Limited just 5 years after graduation, which he then guided for the next 4 years. In 2001, LPL tied up with foreign companies to start Nividu Private Limited to invest in hydropower generation. Anura was the obvious choice to develop his first project at Bellihul Oya, with the entire plant construction handled by Sri Lankan engineers. He guided Nividu Private Limited as manager hydropower for the next 5 years till the middle of 2005, when he decided to get back into academia, where he had been a visiting lecturer since graduation. In September 2005, Anura joined the Electrical Engineering Department of the University of Morocco as a senior lecturer to impart his industrial knowledge to the young undergraduates and guide them in the correct path. He has been a chartered engineer in Sri Lanka since 1996, a corporate member of Sri Lanka Energy Managers Association since 2007, and a fellow of the Institution of Engineers Sri Lanka since 2009. He has also been recognized as an international professional engineer since 2008 and has had extensive international training and experience in Bangladesh, China, Finland, Germany, India, Indonesia, Korea, Myanmar, Norway, Singapore, Switzerland, and USA. Even after he joined the academia, his services were in great demand from the industry. Among these are as Vice Chairman, Ceylon Electric Board from 2011 to 2013, Chairman, National Engineering Research and Development Center from 2013 to 2014, Chairman, Ceylon Electric Board from 2015 to 2017, with parallel posts of Director LTL Holdings Limited, Chairman, Trincomalee Coal Power Company Limited, and Director, Lanka Electric Company Private Limited. When he took his sabbatical leave from the University of Morocco from 2018 to 2020, he was invited and took over the reins as the Chief Executive Officer of Windforce Private Limited from June 2018 to February 2020. Anura has not only been active in industry, but has successfully supervised 2 students towards the Master of Philosophy degree and over 35 students in the research component of the taught master's degree program. He has published widely with publications in 18 peer-reviewed journals and 20 international and local conferences. He is also the author of 3 books on energy. He has been recognized by the University of Morocco for his outstanding research performances annually since 2016. I am pleased to present Professor Anura Wijayapala to you for his inaugural lecture as a professor at the University of Morocco. Over to you, Anura.
Thank you very much, dear Professor Lucas, for your natural introduction of me. And the fine details you have found from the web, my web probably, and even surprised me because you have collected a lot of fine details as well. And once again, thank you, sir. Good afternoon to all of you. Dear Vice Chancellor, Professor Niranjan Muruvardhana, Deputy Vice Chancellor, Professor P.K.S. Mahanama, Dean Faculty of Engineering, Professor Nalin Wickramaratchi, Dean Faculty of Graduate Studies, Professor Aditya Alvis, Head of Department of Electrical Engineering, Professor Wijayapala, Professor Rohan Lucas, Senior Professors, Senior Lecturers, distinguished guests, ladies and gentlemen. I extend a warm welcome to all of you this afternoon. I wholeheartedly dedicate this inaugural lecture to my parents and teachers. Let me share my screen. I don't intend to say anything about myself because Professor Lucas has covered everything. So I don't want to say how my journey towards professorship at University of Morocco. It covered most of things, so I will save time on that. My speech will be on 2 parts. A brief recap on the reality of the economic crisis we are facing today. And then I will go on to present some selected nationally oriented research we have done at Department of Electrical Engineering, University of Morocco. Our economy is in great trouble, as we all of you, us, everyday witness. Our foreign reserves are at all-time low levels. Rupee has devalued so much. We are expecting a high jump very soon when the government releases its control. GDP has plummeted. I am 57 years old. Samudrika, my wife, advises me not to mention age in public. But in my lifetime, I cannot recollect, other than these great sportspersons, any scholar or scientist who brought international fame or wealth that did our motherland justice for its old calling, Pearl of Indian Ocean. Today, the theme of my speech will be the need for aligning ourselves with the national economic growth. The topic I have selected today for my inaugural lecture is to help the country out of present economic precipice, research with the national alignment. After serving the industry for 15 years, I have been with the university academia for yet another 15 years. I have also been the chairman of National Engineering Research and Development Center for 2 years. At both places, I see a surprising low contribution to GDP through research and innovation. It is true that we make a lot of high-level academic publications, which provides us with many citations to be proud of. Can we equally be happy about the contributions our research brought to industry to develop products and services to generate economic value? I read from the banner in this room on the wall of on my right side, quoting Kumarthanga Munidasa, saying, "Alut alut de notanana jatiya lowa nonagi." The nation which does not produce innovative new products does not prosper. Is that not what exactly has happened to our nation today? We are in the worst economic crisis in the country is facing for a good known period. We have a formidable loan portfolio to be repaid. We do not have enough foreign currency even to buy our day-to-day imports, and neither capability of producing alternatives locally to fill the gaps. Electricity and energy sectors are in turmoil. Our food production and farming have not been at such low tide probably for many centuries. I quote from Wikipedia. Baminithya Femini, 103 to 89 BC. During the reigns of King Vattagamani Abaya was a period of over a decade in which ancient Sri Lanka's irrigation system failed as a result of invasion, corruption, and neglect. I repeat, as a result of invasion, corruption, and neglect. Unquote. Now, whom we blame for all these? Probably them, and definitely now politicians. But who are politicians? They are also us, elected by us, failed to deliver to us, and now blamed by us. Us means we are also part of it. Therefore, we should do our duty to bring prosperity to this country, and that can be done only with the rapid economic development. This slide shows pre-COVID economic indicators of South Asian countries. It has been done in 2018. 2019 figures are projections. The economic growth rates are averages from 2013 to 2018. I selected this because it is after the end of the war and combining two governments. It shows how deplorably bad we have been doing even pre-COVID. We are just above Afghanistan because we know how the affairs are in Afghanistan. But see other countries, Pakistan, Bhutan, Maldives, India, Nepal, Bangladesh, they are doing far better than us. So this is how ADP projects economic growth rate for 2022 for South Asia. All these countries had COVID. See where they predict us to be, at the very bottom. And I will not be surprised if we don't achieve even this much of 3.4% with the present power and energy crisis, which are affecting our industrial productions and other service sectors. Before going into the second part of my speech, let me present this interesting correlation between GDP growth rate and electricity demand growth rate. This is my sector. We are in the electricity sector and the energy sector. And we can see from year 2000 to 2020, the GDP growth rate, which is in red, and the electricity demand growth rate, which is in blue. And we can see the correlation. It acts in two ways. One thing is due to incidents like war, or which was in extensively happening in 2009, the GDP and other things went down. Therefore, electricity demand went down. And it happened alternatively also when there's a power crisis. For example, in 2012-13, we had a severe power crisis with power cuts. See, the electricity demand, that is electricity supply, really came down, which forced the national economy to come down, economic growth rate, GDP growth rate to come down. And I'm sure this year it may repeat again because of all these power cuts and energy supply shortages. Again, economic growth will come down. So it's unfortunate. But in the electricity sector, energy sector, we see the importance of our part. So we should provide cheap electricity and with required reliability in order to facilitate the economic growth rate. Vice Chancellor, ladies and gentlemen. With that, I will stick to my talk proper this evening on the research and innovations done at Department of Electrical Engineering by me, together with my students and colleagues. With my industrial background, I could recognize the problems as well as opportunities in the industry, and I tried to find avenues and solutions together with my teams. I have picked those which can make a direct economic impact to the country, and in presenting them, I have avoided technical jargon so that any person can understand and appreciate them. So I have selected out of all the research and project work we have done at our department with my teams, 10 projects to be presented this evening on different electrical engineering supply aspects. The first one I have selected is co-firing of biomass with coal in pulverized coal-fired boilers at Lakuja power plant. This I did with the engineer who is working at the power plant, engineer SRH Mudunkotua. He facilitated a lot because he has direct information about the power plant as well as its subsystems. So we plan to co-fire it with powdered biomass, and then we studied what are the existing technologies. There are 3 technologies that we can use: direct, indirect, and parallel. And after many deliberations, we thought that direct combustion, direct co-firing will be the best option. And this is a typical pulverized coal-fired boiler arrangement. We can see that the red color zone, firing zone, to which pulverized coal is mixed with sent with compressed air. So we plan to add powdered biomass to these burners at the very point where the coal is entering. And we studied different versions of biomass, and because it has to be continuous supply and sustainably grown, we selected Glycidia, which is a famous biomass in Sri Lanka, fast growing, and also can be processed easily. And we compared with coal and found that it is very suitable to be added with coal to fire the boilers. And we looked at the possibilities of transporting them, any restrictions and cost implications, and we found that even if we transport in the furthest corners of Sri Lanka to Putlam, it still makes economic sense. And then we looked at the land requirement and other things. If we grow them as monocrops or intercrops in coconut cultivations, for example, and found both can be applied, of course, depending upon the opportunities for the suppliers. And as an example, as a start, we thought of replacing 5% of coal of Lakuja power plant, which means a requirement of 165,000 tons of biomass per year. At a 5 rupees per kilogram moderate price, this will translate to 825 million rupees, which will go to farmers and other rural economies because they will be the ones who will be supplying biomass. And we can do it either with 16,500 acres of dedicated biomass plantation or 40,000 acres of intercrop or a combination of them. And we designed the system of processing, and also we designed how and where the biomass should be added to the existing coal firing system. And the black lines are the coal firing system. Blue lines are what we proposed to bring compressed air, biomass with compressed air with the same pressure and add to the coal lines, and then they enter the furnace layer where the flames are converting the biomass and the coal together to heat energy. And economic sense was we worked out 2.5 years, the expenditure requirement of 250 million could be easily covered. And this makes more sense now because you can see these are the prices of price of coal from 2009 to 2022, and the prices are in dollars per ton. And you can see the since 2001 with the COVID implications and other supply demand mismatches, coal prices together with the other energy source prices have rocketed up. Earlier it used to be on average about $65 per ton. Now it has gone about $200 a ton. So I learned that recently Lakuja purchased about $200 a ton coal prices. So I'm sure that, but these prices, these high prices will not remain for a long time. With the supply demand again readjusted, they will come down. But I'm also sure they will not come down to the previous low levels. They will stay above the previous low levels. So this makes a more economic sense. We made a publication on our research, and also later, after 2 years of the research, I found that a UK utility takes next steps to convert coal units. I read the first line of this article. UK utility Rex Power last week said it has taken a 4th coal-fired power generating unit offline at Rex Power Station in North Yorkshire in preparation to convert it to run on biomass. Remember, it is not part mixing. It is complete conversion to biomass. So if we make that, if we are able to do that, we can replace 2.5 million tons of coal a year, which will translate to even at say, assuming $100 a ton, it will be say 250 million US dollars to our local economy if we can retain that. So these are the challenges to be taken by both the government as well as the CEP, engineers and agriculture and everybody, the farming, energy plantations and all these things. So if this is successful, after our tea, rubber, coconut plantations, energy plantations will come and strongly take over our supporting our economy. The second project, the second research I want to present is development of a mathematical model to predict daily demand of electricity based on weather parameters. So this I did with my co-researchers, Dr. Tilak Siambalapidia and I.N. Jayasekara, is an engineer from Ceylon Institute. And this load curve, this is the demand curve. This, of course, is a little old because this is relevant to the period where we did the research. And but the shape remained almost the same. This is our daily demand curve. You can see early morning hours where the demand is very low, and then the morning there's a peak when we stir up in the morning, putting our kettles and all these things on the network, and then day demand and a huge evening demand. The red curve corresponds to a dry day in the month of May 2013, and the black curve on the same month, on a wet day. Both days are working days. So similar demand should exist. But we can see from a wet day to dry day, there's a significant difference in the demand. So if the CEP system control engineer knows this going to happen tomorrow, day after tomorrow, even afterwards, then he can plan this generation accordingly. If you put into the context of today, then he can plan his power cuts accordingly. So he can say on the day after tomorrow, power cuts will be only 3 hours because it's going to be a cool day, depending upon the weather. So that will be a handy prediction for them. And we looked at how to predict this, and then we looked at the available weather parameters, because all these depend upon the weather parameters like temperature, ambient temperature, humidity, wind direction, wind speed, etc. So when we looked at, there are plenty of predictions, accurate predictions available on all these things. 3-day predictions, 5-day predictions, even 10-day predictions. So we can easily use these parameters in making a model. So based on that, we try to make a model, and we find that the weekdays are different from Saturdays and Saturdays are different from Sundays. So we have to build 3 models here. 24 equations for 24 hours of weekday, and similarly for Saturday and Sunday, which we did this way by multiple linear regression using these parameters. And this is the model that we built, a few equations of the model that we built for working day, similarly for other days. And so see, this is the validation of our model. You can see the black curve here is the actual demand of electricity on a certain date, February 3rd, 2014. Then we predicted it, say the green one, 4 days ahead, green one. And then the blue one, light blue one, 3 days ahead prediction based on weather parameters. And then the purple one, 2 day ahead prediction. And the red one, 1 day ahead prediction. As you get more and more accurate data. You can see almost all of them are pretty good enough for the utilization. So you can see even 4 day ahead prediction can be used handily by the system control engineer in predicting the 4 days ahead demand, and accordingly he can say to power plants, I don't want you on this day. We can manage without you. Take your say scheduled maintenance on that day. Or else nowadays he can say this day our demand is this, therefore power cuts will be shorter or longer. So likewise. So this model will be useful to anybody working in the system control center in managing the dispatch schedule. We made a publication on that also in the Journal of Institution of Engineers Sri Lanka. Third one I want to present is optimization of the usage of Tamanlava water reservoirs for power generation. This I did with the engineer who was working with Mr. Engineer Patiraja, who was working at Samanla Power Station. We all know that this is a beautiful aerial view of Samanla Power Plant, Samanla Reservoir. And you can see, as we filled water in 1992, a leak developed about 53 meters below the surface water level. And many efforts were done to close it. And this shows the red line shows the leak rate in cubic meters per second, while the blue line shows the surface level, reservoir surface water level above mean sea level, which is on the right hand side, 400 meters plus and so on. And on the left hand side scale, you can see water leak rate in cubic meters per second. And first few years, for about 1997, they tried their best to locate the leak and close it. They spent about 10-15 billion rupees for a wall of injected grout to close it, where they think that the leak could exist, but it completely failed. Then in 1999 period, they did a wet blanketing operation. This we know very well because the operation was carried out by the Lanka Transformers Group. So that means we took soil, suitable soil, and dumped into areas where the leak possibly existed. And it improved. You can see immediately afterwards, leak has reduced. Leak reduced by about 60% of the previous value. But unfortunately, in 2007, after so many years of a low leak rate, they thought that sorry for that. I pressed the wrong button. They thought they can fill the reservoir a little more. And you can see that they tried to fill it, and then the leak jumped up. Red line jumped up and settled to a new value of about 2.5 cubic meters per second. Even today, the leak is at that. So over the last 30 years, all the efforts to close this leak has failed. Then we looked at the problem differently. So we brainstormed with my engineers, my colleagues, brainstormed and looked at how we can do otherwise to stop this wastage of water. Then we considered this fact. The surface water level is about 440 meters above mean sea level. And the leak is at 387, about 53 meters below the surface level. Whereas the power plant, Samanla power plant has a 320 meter head, that is 320 meters below 440 meter surface water level. So that means, so we thought, why not pump back the water 53 meters, and to every cubic meter so pumped back can go through the power plant with a 320 meter head. So it looked to us sensible. So we did the calculations. We designed the leak pump back system, and then looked at how much energy is required to pump water back to the reservoir. So, but we can't pump back all the water. We have to let the irrigation water flow through the Wallaby River. So subtracting the minimum water requirement of the river, we decided to pump back the balance, and for which we need 11.3 gigawatt hours, so 11.3 million units. And then the same water, when runs to the power plant, as you can see in the bottom there, can produce 59 or approximately 60 million units. So which means we can have an excess of 48 gigawatt hours if we do this. And if we, now this is dispatchable energy, that is, in the reservoir water. So we can dispatch them in the evening when the electricity generation is most costly. For example, GT7, which is serving the peak in the evening at Kalnith, cost about 40 rupees per kilowatt hour. So at this rate, if you calculate the value of this water, it translates about 1.9 billion rupees every year. And then we designed the leak pump back system and found that the cost to be less than 1.5 billion rupees. So it is less than 1 year's payback period. And so every year for a very long time to come, 1.9 billion rupees, so nearly 2 billion rupees in today's energy terms will be available to CEP and to the nation. And we made a publication on this in, I think it was in Mercon 2016. The fourth research out of the 10 I am presenting this afternoon. The fourth one is mitigation of lightning surge stresses in the high voltage windings of distribution transformers by introducing an electrostatic shield. I did it with engineer H.S.C. Karunanandan. And you can see in the left bar chart, we can see that the number of transformers failed in CB region 3. CB has 4 regions. This is region 3 data. And you can see transformers failed due to a variety of reasons. So, but you can see when you look at April has a substantial increase in the failures. And it is due to, as we all know, the high lightning and thunder. As we all know, April is a month we get a lot of lightning and thunder. And so these additional failures are mostly attributable to failures by lightning surges. Then we looked at the right-hand side graph is very famous in our electricity theories. Professor Lucas used to teach us, Professor Sam Karunanandan used to teach us, and you can see that there are 3 curves, how the surge voltage will spread across the transformer winding from the line end to neutral end. And you can see when this parameter called alpha is 10, on a few number of turns, large voltage quantity appears. Large voltage drop is there. But as alpha is 0, you can see the voltage is more uniformly distributed. Therefore, the chance of initial turns getting failed, insulation failed, is less. So we looked at how to apply this. We proposed an electrostatic shield between the last layer and the next layer. That is simply an aluminium foil to be connected to ground. And then we modeled the 2 circuits with and without the shield for a 160 kVA transformer with the data from Lanka Transformers Limited. And you can see the shield in the winding, the black layer. And accordingly, the CG and CF. I forgot to tell you, in this graph, this alpha is really square root of capacitance to ground divided by capacitance to the interwinding turn to turn capacitances per length. And so by decreasing capacitance to ground, we can decrease alpha or this parameter. And that is what we try to do. And so by doing this, we simulated this and then found, the bottom graph shows the voltage distribution, surge voltage distribution along the transformer high voltage winding without the shield, which shows in 5% of the winding, about say 15-20% of the voltage is distributed. Whereas when you have the shield inserted, the above one, you can see very uniform distribution. Even at 10%, it is a very small quantity of surge voltage that will appear, that will prevent the turn-to-turn insulation failure when the surge enters the transformer winding. So we again made a publication on that, and then we discussed with Lanka Transformers, and they started to introduce this shield initially to private customers. Still, CEP has not accommodated. If CEP engineers are listening, I invite them to check this, look at the test data, and to introduce this to your transformers as well, which will be immensely beneficial in reducing the transformer failures. And for the private customers, now Lanka Transformer has introduced this. So the aluminum shield appears just inside the last winding layer. So, and it is grounded. So that's the idea. And the 5th research outcome I want to present is effects of electromagnetic fields due to high voltage transmission lines on detonator firing circuit. This came from a batchmate of mine who works at GSMB, Geological Survey and Mines Bureau. They have a problem that, that this is the way they rock blast. And they drill the rock and then insert the electric detonator at the bottom and then the gelignite charge and then cap it. And then take the 2 wires and they connect many of them in series and with a dynamo they apply a voltage to blast it. That's the normal practice. Now they find when they do this under transmission lines, inadvertent firing takes place, endangering people's lives. So they asked us, can you work out what are the safe distances from the transmission lines where we can do this operation safe? So we simulated that, and we also did laboratory experiments, and then we did field testing. Of course, GSMB bought the necessary equipment for us. They are still with us, our laboratories. They donated to us. And then we did simulations and then came out with these safe distances. For example, 220 kV transmission lines, we said from the center line up to 40 meters, if you have your detonators, there is a 80% chance of inadvertent firing. So we said avoid that and then you will be safe. So they are using this data and they have given it to the industrials also in this business. But if they really have to do under transmission lines, they have to construct a shield and do it. Then electromagnetic penetration will not be there to fire the circuit, but that is an additional cost. We again made a publication on that. Sixth project that I want to present is technical, environmental, and economic feasibility of introducing added storage to run-of-river mini hydro plants to improve dispatchability. And again, I come back to these load curves. Of course, I have put the load curve evaluation also from 2013 to 2020. It doesn't matter for my explanation, but we can see in the evening there's a big peak. For that, you need dispatchable power plant. Dispatchable power plant means when the system control engineer tells by a telephone call also that I want 100 megawatts from your power plant from 6:30 p.m. to say 11:30 p.m., then the power plant is able to do it. This can be done by large hydropower plants with reservoirs and also thermal power plant. But run-of-river power plants, most of our mini hydropower plants with a total capacity of 400 megawatts are run-of-river power plants, where if there is river water in the river, power plant can generate. Otherwise, it cannot generate. So they are not dispatchable. They are not dispatchable. Therefore, we investigated, can we make them dispatchable by collecting water, especially in the dry season like these days. So we did this two sample projects, Bulakwatta and Batatota. One is in Haputale, one is Kuruvite. Both belongs to Windforce Private Limited. So I had connections with, that's why I selected them. Then we designed a modification to the weir to raise as much as possible the weir and collect water at the weir without having the backwater curve increasing too much, inundating upstream lands. So here we proposed a 3.5 meter increase without much of an environmental impact, and which could help this power plant to collect water without running all day, collect water and run 3 hours. 3 hours on full load during the evening, or maybe 3 hours separately during morning peak, day peak, or evening peak as appropriate. So we did all these designs, and then we presented a paper also. And this concept is suited Upper Kothmale power plant. It has a small pond, 2.5 million cubic meter pond. So they collect water and run 155 megawatt full capacity in the evening, providing valuable peak power where the demand is highest. And this is the publication we made in I think 2018 Mercon. And the seventh research I want to present is evaluation of the techno-economic benefits of shifting air conditioning loads from evening peak to off-peak hours as a case study for Cinnamon Lakeside Hotel. And this is, when we studied the hotel, this is their chillers electrical load profile. So it grows in the evening, from 15 hours to about 18 hours the maximum, and then also a high value, and in the morning hours low demand. And then we proposed to, sorry, then I will refer to this the tariff CB applies in hotels, which I have marked with red pen. You can see hotels have a mandatory time of day tariff. So during the daytime from 5:30 in the morning to 18:30, 1465 rupees. Peak time 18:30 to 22:30. It is very expensive, 2350, and off peak very cheap, 980. We wanted to use this fact. Cheap, the electricity is cheap in the morning hours. So we proposed run the chillers more, the existing chiller more in the early morning hours when the electricity is very cheap, and store cold water, cold storage, chilled water storage, and then don't run the chillers during the evening hours where the electricity is expensive from 6:30 p.m. to 10:30 p.m. Instead, use the stored chilled water. We looked at many possibilities, but found this is the cheapest with the IRR of 40%. Other options were to have a separate chillers and all that, and also to use the daytime also replaced, but which didn't prove to be very attractive financial. So this is the best option. So we invite other hotels to also to use these facts and to invest a little. So this requires only 10 million rupees. So you can see we can get the long-term benefits for a hotel or other industry by employing this. Again, we made a publication based on this. The eighth research I want to present is one I did when I was at Nerd Center together with the engineer there, Hemanta Kumar. And what we planned is a micro turbine, micro electrical system, or without any grid connection, which has a generator, wind turbine generator, and a PV panel and a battery, and which can supply. We did a pilot project with 100 watts, like a small case, because we had a small wind turbine, and we used a 60 watts panel. This is for the demonstration only, and therefore then we found that we use a Homer software from National Renewable Energy Laboratory of USA for the optimization, and we came out with the 60 watts panel, solar panel, and 100 watt turbine. This was available at Nerd Center, so we fixed that capacity and optimized the other two, and 70 ampere hour lead acid batteries, 4 numbers as the support. So we can have with a very high reliable micro power source for a place where the grid is not available. So this can be scaled up at different costs, but it is useful where the grid cannot extend and supply electricity. Again, we made a publication, and for that we received the best paper award for the journal engineer in 2016. And ninth research out of the 10 I am presenting is the economic comparison of reservoir type and runoff river type hydropower plants, a case study for Upper Kotmale hydropower plant. You know that reservoirs are not thought of as very environmental friendly due to a variety of reasons, because it stops water for the downstream, and the entire downstream ecological system is affected. And also, recently the scientists found that they are methane emitting sources because of the flooded plants in the initial case, and also the plantation, the other things that flow into the reservoir. All these things decay and finally end up emitting methane into the environment. And that has a cost, greenhouse gas cost. So in comparing the two projects, the previous project was called Caledonia Reservoir Project, which was going to have a larger capacity power plant, 214 megawatt power plant. But due to environmental reasons and the protests on the politicians and the people, this was converted to a runoff river power plant and now executed, and to be a 150 megawatt power plant. And then we compared these two options, combined with the impacts of emission. We modeled and calculated how much methane it would emit, and then costed that about say $30 a ton and so on. And then we calculate the levelized cost of electricity, which is in the bottommost slide for the two power plants, and found that for the Reservoir Caledonia project, it is for the same year's cost 1538 rupees, whereas the Talwakale Reservoir ROR project is only 11.17 unit cost. So comparatively, therefore, reservoir type projects are also good. Only disadvantage is we lose some capacity, 240 megawatt against 150 megawatt, and also dispatchability is limited, but unit cost wise, the run-of-river power plant seems to be more attractive. And again, we made a publication, and for which also we received the best paper award for the journal in 2018. And the last project I want to present is the automatic load balancer for distribution transformers. This we did as an undergraduate project. Professor J.P. Karunadasa, myself, and engineer from CEB, engineer Fernando, supervised this project. And of course, this is a combined project. Engineer Fernando did the master's project with this, with simulation. But with the undergraduate project, we did the physical construction part. And this is the problem. You know that when you take a distribution transformer, it is impossible to balance the three-phase current. A distribution transformer on your roadside has three phases. So three phases carry currents. So here we have termed them IA, IB, and IC. You can see in this case, IC is pretty high compared to others. So we can't utilize the transformer fully. One phase gets fully overloaded before other phases. And what CEB and LECO do is, say periodically, every 6 months or yearly, they will try to shift the loads, so houses, from the highly loaded phase to a low loaded phase. But this is a never 100% successful task. One thing is the loads, that customer loads vary. And also nowadays it is more aggravated by the presence of solar photovoltaic generation on rooftops. So it is not possible to do manually in a perfect way. So what we proposed is, to, the source is the transformer. We want to keep the three currents in the transformer equal. That is our target. So what we thought is, but the load currents can be different. Load currents can be high, medium, or low. So what we thought is, rather than coming to the source, to supply currents to the inverter system that we designed, or the automatic load balancer, to the high load required phases, and to draw currents from the low phases, low current phases, to our system, and then have a DC command bar from which to invert them to AC and to feed the necessary phases. And our students constructed this unit, the inverter systems and this automatic load balancer, and demonstrated. And this is the outcome. You can see the topmost one before balancing. You can see the purple phase has the higher current, green one and red one lower, but all different. Then you can see the second one from top. You can see after few cycles, our automatic load balancer balances all three phases, which will facilitate CEB to utilize the full capacity, or LECO to utilize the full capacity of the transformer without any violation of the loading conditions of the phases. And this was published in Sri Lanka Power Engineering Conference 2021. And out of all the undergraduate projects that were presented there, this won the first place in 2021. Ladies and gentlemen, I have presented 10 cases to you, and then I have disseminated my knowledge with what I have gained in the industry as well as in academia by writing a book on rooftop solar PV systems, which include the financial analysis. So if you really want to look at whether the investment is worthwhile, there's a chapter how to do an economic analysis of your investment. And then I have also shared my knowledge with the hydropower industry by writing the book called Development of Small Hydropower Plants, Practical Information, which I later translated to Sinhala, because there are a large number of people working in a small hydro sector who are not very conversant with English. So this Sinhala version is also in high demand. Many people have used it. And many engineers have commented to me that when they design hydropower plants, they refer to my book. So I'm very happy on that. And I have also disseminated my knowledge in participating in more than 25 TV debates, discussions, and interviews, where I have shared my views on power sector and what should be done, what should not be done, etc. And I would also like to recollect, as the then president of the University of Moratuwa Teachers Association, that we supported the introduction of the research allowance in 2012 while engaged in the several months-long trade union actions. Unions from some other universities, I will not name, were totally against in connecting the performance to salary, but we insisted it should be there. When we look back over the past 10 years, from 2012 to 2022, we see a marked increase in the number of research publications in all universities. All of us can be happy about it. To get the research allowance, we have to have at least one acceptable publication. A professor is paid nearly ₹500,000 as research allowance every year. It's a pretty big amount. Now I would like to further propose, if our Deputy Vice Chancellor is listening, who is the chairman of the committee approving the research allowance, to include a new condition to say that the research publication should be in one way or the other contributing to the national development. This is of course more than justifiable as our salaries are paid out of the consolidated funds and finally sponsored by the people of this country. With this, I would like to present my last slide, which shows the mentors and the supporters of my life, my grandmother, my parents and teachers, and in the university, Professor Sam Karunaratne, Professor G.T.F. De Silva, and Professor Lucas, of course. And then after graduation, Engineer U.D. Jayawardena, who was my first boss, and also he was my last boss because I stayed with him for 15 years. And then late Professor H.I.R. Pereira, who was the head of the department, who recruited me into this department, and also until his demise, he was my best friend. And also Professor K.K.Y.W. Pereira has been my teacher, as well as my mentor, and also always sharing our views as we worked in the industry and also in the ministry, in many teams and under various ministers working together. And Professor Lucas has been in the entire cross section, even before in the university as well as after graduation. With that, let me conclude my presentation this evening. Dear Vice Chancellor, ladies and gentlemen, I thank you profoundly for spending your valuable time to listen to me this afternoon. Good evening, good night. Take care during these difficult times. Thank you.
Thank you. 10 projects of national relevance, and how many of that 10 have been actually been integrated?
Some of them, yes. First, and so I asked the CB people to listen to
Right, maybe we should tell that we had to run the generator in anticipation of the event that we are running the journey, because otherwise you never know the power cuts coming now. So it's my pleasure to invite Professor Nali, Dean of Faculty of Engineering, and the program of the session, the mentor to Professor Anura.
Thank you. Thank you very much, Professor Anura Wijayapala. One thing that came to my mind while listening to Professor Anura, one of the major criticism leveled against university research is that they are not nationally relevant and they do not contribute to the nation, while research is done for the sake of research and without any relevance. But today we heard and learned from Professor Anura many research that are actually solutions to existing industrial problems. All of them are the problems that Sri Lankan industry faces. And not only he has solved, some of them have been already utilized in the industry. So congratulations and thank you very much. And we have a little, as usual, a little memento. Thank you very much.
Thank you. With that, another inaugural lecture comes to a close, and till we meet again next month, thank you and have a good day.
Additional part करता है कल के करंट